Thanks, Marta. Yes, now this morning I made a survey of stellar black holes that we can detect beautifully from the LIGO Virgo Cagra interferometers. I want to just spend a few words on this. In the future, also with third generation, but also in the next observing run, we will discover many, many black hole binaries because we have understood that they are dominating the population of gravitational wave sources. And I think that all of you PhD students have to be aware that measuring the masses, the spins, and the luminosity distance across all cosmic ages, as you can view from the beautiful image of our universe, it's really outrageous because we will never measure the mass of a star in a galaxy at redshift 7, but we can measure a black hole binary mass at redshift 7. And so we can sort of then reverse engineering and learn a lot about the initial mass function of stars and how stars and light started to fill the universe. So the beauty of these measurements has to be really understood and appreciated deeply, deeply. Let us now move to my second lecture, and I will start with the supermassive black holes to then return back to light black holes. Here is the outline. I will really carry on a brief overview of the supermassive black holes as we see as active galactic nuclei, that is, we see from the light which is emitted by infalling gas, because this is the way to introduce the concept of black hole seeds, the seeds upon which the supermassive black holes have grown. And I would like to make some personal comment on the potential connection between the stellar black holes that, as I said this morning, their mass can extend slightly above the pair instability gap, but in reality, we are talking about black holes of 10 up to 50 or 60 solar masses, and the very massive ones. What we know about black holes, the supermassive black holes, is from the light they are emitting when they are accreting gas, and probably this is apart from the beautiful image of a jet launched in an active galaxy. The picture I invite you to have you in mind is a supermassive black hole, say of 10 to the 8 or 10 to the 9 solar masses, the one that were discovered at the very early times, surrounded by an accretion disk. If the black hole is spinning, is launching a jet, is surrounded by clouds, the so-called broadline region. Let me say that the type of measurement we are making is the measure of the bolometric luminosity emitted by this system from radio to gamma rays if they are radio loud, or from the optical and the X-rays if they are non-loud in radio. And so it is a measure of the mass accretion rate, which is dictated by the environment, and the efficiency to which gravitational energy is converted into light this eta. And we have an upper limit, which is the famous Eddington luminosity, which is linear in the mass of the black hole. And it's telling us that above this luminosity, you can't have any more stationary spherical accretion because light is pushing the gas out because it's exerting a pressure. The measurement of the mass of the black hole occurs through a very complex procedure, astronomical procedure, by studying the motion of the clouds in the broadline region. So we know with an uncertainty that can be large, a factor of 2 or even more, the mass of the black hole, and the Eddington luminosity gives just a lower limit to the mass of the source that we can detect from light. Interestingly, as I already mentioned, if this is in blue, the average star formation rate in the universe, which has a peak at redshift 2 when the universe is 3 giga-years old, well, also the rise of the AGN activity, which is associated to accretion onto what we presume is a supermassive black hole, because from the time variability and from the luminosity that are emitted, we need a very deep gravitational potential well to explain this. These, as you can see, are really sort of co-evolving. So it means that when the bulk of the star is forming in the universe, also mass is conveyed into a tiny region of 100 parsecs or less to fuel an active galactic nucleus. Now, the activity in nearby galaxy is almost quenched. We can talk about dormant black holes in galaxies today, whereas the star formation rate is still ongoing. When the black hole is dormant, we can measure the mass in nearby galaxies by exploiting the ability of resolving stars within the sphere of influence through kinematical measurements of their velocity. And here is just the beauty of the galactic center, which is hosting a 4 million sun solar mass. And these are the S stars that were, this discovery was awarded by the Nobel Prize this year. Sagittarius A star is a weak radio source. And so let me say that we discovered our black hole by looking at the dynamics of stars that are orbiting on elliptical, nearly elliptical orbits around this dark massive object that we believe it is a black hole candidate. In 2000, there has been also an important discovery that was sort of unexpected by the astronomical community, because the black hole, as I said, has a Schwarzschild radius that is of 300 typically or less astronomical units. So a billion sun within the solar system confined. So it is a very exotic object. And the sphere of influence is really very small compared to galactic dimensions that are hundreds of kiloparsec or kiloparsec. The distance from the center of the sun is 8.7 kiloparsecs. And the astronomers has found a correlation between the black hole mass and the stellar mass. So the bigger is the galaxy, the bigger is the black hole. And also a tighter correlation, which is telling that the bigger is the stellar velocity dispersion, which is measuring the depth of the potential well in any galaxy of the universe, correlated with the mass of the black hole, or they say the mass of the black hole scale as sigma to a power which is extraordinarily high, between say 4 and 5. And this was a surprise, but now we understand that this correlation is established when the black hole is active, is injecting into the interstellar medium kinetic energy and light, so that it can self-regulate the star formation content in the galaxy. And this really, it is really a very, very important correlation, because also when we know the mass of a galaxy, we can presume to know the mass of a quiescent black hole. So this co-evolution, symbiotic evolution, has been quite relevant, because also the astronomers that were studying just the AGN had to consider that they are really living in galaxies, and forced to have a cosmological view of their growth and evolution. Please notice here that the bulk of the observations are selecting the most massive black holes of, say, above 10 to the 6, but the bulk of these black holes have masses between 10 to the 8 and 10 to the 10 solar masses. So huge black holes in huge galaxies with huge stellar dispersion velocities. And then when we move down here, there is a sort of a spread in the correlation, and there are maybe only upper bounds. So we have not much information of the black holes like the Milky Way black hole or Lytle black hole, say of 10 to the 5 or 10 to the 4. In a very nice review by Green, I got this collection of new results which extend observations to the low mass tail of the supermassive black holes in nuclear star clusters. The nuclear star clusters are just a high concentration of light in the midst of a galaxy. And clearly you see that there are black holes in nuclear star cluster, these squares, okay? There are black holes in the so-called UCDs, ultra-compact dwarfs, but still they are somewhat massive. And then there are black hole of 10 to the 5 or candidates. They are very difficult to measure dynamically or because they are dim in luminosity. And so there are upper limits. So we believe that the low mass end of the mass distribution is populated, but it is very difficult to get from electromagnetic observations. And so returning to my favorite view of the two families, this drop is maybe a fake, so it's not reality. And as in this review by Jenny, you can see, we can extend the mass function, so or the mass density of black holes down to 10 to the 4 and 10 to the 6, if we include knowledge about these light black hole in nuclear star clusters. And we have to make a hint on the occupation fraction in these galaxies. While massive black holes are almost ubiquitous in the very bright massive galaxies, when we go to the dwarf scale, we don't know whether there is or there is not a black hole. And so if the occupation fraction is large, we can even have furthermore light black supermassive black holes than my simple cartoon was indicating. And also there might be wandering black holes, and I will return in future. A key observation was that when we look at the population of active galactic nuclei using X-ray light, and we also study the X-ray background that is pervading the universe, we can do the following calculation. We measure the luminosity, but if a black hole is accreting at a given luminosity, which is dictated by m dot and the efficiency, it is also growing with mass. 1 minus eta, the efficiency, goes into growing the mass of the black hole. And eta depends on how the black hole is fueled. I don't want to say more, but it is uncertain, between 10 to the minus 2 or 10 to the minus 3, up to 10%. So light means mass. And if you count all the X-ray light that is pervading our universe, you can convert in a mass density increment that black holes can experience due to accretion. And you find out that this mass increment has this value. With this, this epsilon, is eta, is the efficiency. Sorry, I didn't use the same notation. So light is mass, and then we understood that black holes are acquiring mass through accretion. And now, if I'm using these relations, I can compute the mass density in the quiescent 2-day galaxies, because this is a measurement of the 2-day black hole in the bright galaxies. I discovered that the mass density in dormant black holes at redshift 0 is comparable to the one that comes from light, and this is an independent measure. So we have learned that supermassive black holes have grown at least below redshift 3 in mass due to radiative efficient accretion. When we look at the population of accreting black hole, then if they have accreted a lot of mass, also we can say some few words about the spin evolution of the accreting black holes. So let me just remark that this morning we have seen stellar black holes whose spin, unless they were product of a merger, is the spin at birth. Here, instead, we lose memory of both the initial mass and the initial spin that the black hole had at birth. They had to be lighter because, of course, 10 to the 9 solar masses cannot be confined within a solar system in a radial spherical collapse. Overall, in the universe, there is angular momentum, which prevents. So there is a slow growth, but a growth of order of magnitudes. So I can have a black hole of 10 to the 4 and then form up a black hole of 10 to the 9 solar masses. So 5 order of magnitudes. And the spin can increase from 0 to 1, the maximum spin, just accreting the square root of 6 if accretion is prograde, or it can span down by accreting a comparable mass of gas. And in addition, accretion torques reorient the spin. So the spin for supermassive black hole is a way to gauge their accretion history. And let me just mention briefly the physics in 5 minutes in a nutshell. Really, suppose you have a black hole, a supermassive black hole, with an initial spin, which is surrounded by an accretion disk inside a galaxy. You know that if these fluid elements, consider them as sort of test particles, they are subjected to the length-theory precession. And so they would really precess, but since they are fluid, dissipation in the fluid is such that within a radius, which is of the order of 500 Schwarzschild radii, for a maximally spinning A, here is the spin of the black hole, align in the orbital plane, in the equatorial plane of the spinning black holes. So they would precess, but the precession above the plane causes shocks, and so that the minimum energy configuration is that of a disk in the equatorial plane of the black hole. But at some point, the disk is extending and there is a so-called warp. And the interaction of the outermost region, here you see a clear warp in the fluid elements, then if you apply standard fluid mechanics, you find out that the spin of the black hole is increasing due to the mass accretion rate, which, because all fluid elements accreting at the rate m dot are depositing the angular momentum at the ISCO radius, and a precession term which led to black hole precessing. But after a precession, a few precession, again viscosity can align the spin to of the black hole of the disk if the disk is very massive. And so at the end, we have a rise in the spin and an alignment. And this is really true if we have continuous coherent fueling for many order of magnitude in the mass accretion rate, so in the increase in the mass. And so we expect that if the accretion is prolonged and continuous, black holes are really spinning very rapidly. But instead, if the fueling is chaotic, well, the spin can move up and down depending on the orientation of the disk. And so you can have retrograde accretion, which is spinning down, prograde accretion, which is spinning up. And so if we would discover a population of spinning black hole with all spin 1, we would know that accretion was continuous and very efficient. And measuring the spin, this is a plot of the spin that has been measured in active galactic nuclei. It is a very delicate measure, very complicated, usually by studying the shape of the iron line. Having said that, I skip this. Now we know a lot about the AGN population from the luminosity and from accretion. But what is remarkable, and these are discoveries of the recent years, is that we find quasars, powerful quasars emitting 10 to the 46, 10 to the 47 ergs per second, when the universe was only 7.9, say 1 giga-years old. So we have a bunch of quasar out of redshift 7 near to the redshift of cosmic reionization. Here, the galaxies are forming. And so how would it be possible that these gigantic black holes are in place when we are just at the beginning of the star formation history of the universe? How do they form? And well, then I leave this as a summary so I don't repeat what I already said. It is clear that if the supermassive black holes have grown by accretion, they come to birth lighter. And so we call seed those intermediate mass black holes forming at high redshift because we want to explain these very massive and early forming quasars, forming probably in the most massive galaxies that are present at that redshift, 7, and there are not many. And this has to be a process that is really short-lived. So I like to call the seed as transitional object that might form in a single epoch, and that they later grow by accretion and merger. Accretion and merger that erase information on their birth properties. There is an active ongoing research on thinking at a new channel for forming these black hole seeds that might not have any relation with the stellar black holes. I just mentioned 3 models. The light seed coming from population 3, this morning I said that given the zero metallicity, stars may be heavy because fragmentation is weak in the gas cloud, and we expect this range of black hole seeds between 150, so say beyond the pair instability gap, and say up to 10 to the 3, but this is just a pure speculation, forming in metal-free or halos with very low metallicity, whose virial temperature, this is the temperature of the initial forming gas clouds with little dust. What? Okay, and I stop here maybe in a moment. And then in halo of 10 to the 6. And then there is the very nice and interesting, but maybe quite rare process, which is called heavy seeds. These are seeds that come from the direct collapse of very massive gas cloud in atomic cooling halos, contrary to molecular cooling halos that can lower the temperature to form stars. Here you don't form stars. You have the coherent collapse, direct collapse of a gas cloud in an atomic cooling halo with a high virial temperature. But in order not to fragment, this forming direct collapse scenario requires that the galaxy is, the region is illuminated by a very intense UV flux so that you avoid fragmentation. And the last, and then I stop here, with Marta, we have been working a lot on, no, not a lot, but we have been working on the so-called runaway scenario for these seeds. So notice how the heavy seeds have masses between 10 to the 4 and 10 to the 5 solar masses. The one, the black hole that we would like to detect in the dwarf galaxy in the nearby universe. And instead, in this intermediate scenario, we have still black holes of 1,000 solar masses that form through the collisions of stars in dense nuclear star clusters in forming these galaxies. And remember this morning, I was just depicting this scenario in which you might form an intermediate mass black hole simply by merging stars through binary evolution. And it would be very interesting to discuss this, but this is just, I gave you the flavor. And I stop here to get the first questions.
Okay, so if you have any questions, you can either put them in the chat or can raise your hand. Chiara, do you want to unmute yourself and ask the question?
Thank you. So if I understand correctly, then with respect to the cartoon that you are referring to also this morning, right, in which there are the stellar origin black holes, there is the pair instability gap, and then there are the supermassive black holes, and there is this decrease, right, towards the pair instability gap.
Yes.
So you said that this decrease might very well be an observational bias.
Exactly.
Okay. So and it can actually rise. Now, if it rises, I suppose at some point you will connect this with the mechanism of formation.
Exactly.
Of the,
exactly.
Right. So it will then connect with the yellow part, let's say with the the stellar orange black holes, only if you assume that these black holes come from POP3 stars.
Exactly.
Otherwise, they will be completely separate.
Otherwise, let me say that if the direct collapse scenario is correct, so the heavy seeds, this is something new. It is the collapse of a gas cloud. It is a relativistic, general relativity controlled collapse, but of a very tenuous, say, object compared to instead the nucleus, the core of a star, and would be completely different. If it is the runaway, at the end, you form the massive black holes from stars. And this is indeed the point I would like to raise, and you anticipated to me. So I'm fascinated by this possibility, because maybe the very super massive, giant, obese black holes are come from a unique seeds that are the stars, that we know how they form and how they evolve and how they collapse, besides details, okay? And this is fascinating. So really, maybe the only collapse is just a black hole of stellar origin. And then you make sort of in a Lego assembly, you make the very big one, then allowing them to accrete and merge. And so really, this black hole desert can be filled, and we would like to know how, and to probe this scenario. And sort of, in a sense, also to probe what I like to call the universality of black holes. Because if also these black holes are really Kerr black holes, as the stellar ones, there is a sort of really an outrageous result of general relativity. But we don't know if there are in the middle here new mechanisms that are explaining the very massive ones, or they are straight away coming from stars. So, and in this cartoon, I was trying to really say, seeds are in this range. We would like to have them relatively massive, because otherwise they cannot grow by accretion significantly. So if you take a seed of 200 solar masses and let it go through accretion, he has to really accrete a lot and continuously, which is not obvious at all. And at the beginning, the sphere of influence of this black hole is small. So how can he attract mass? If it is an heavy seed of 10 to the 4, it has a much larger sphere of influence, and it can accrete more easily. The stellar collision scenario is in the midst. And also there is the claim that massive mergers can convey so much mass into the nucleus that you can build up a very massive black hole of 10 to the 6 solar masses. But no more than 10 to the 6, because, you know, there is a lot of angular momentum in the universe, and so it's not a spherical collapse. So we need building blocks that then has to be detected and has to evolve through, let me say, accretion and mergers. How can we detect the seeds? Maybe the audience is not fully interested in this.
Wait, Monica, we have 2 more questions first.
Great.
Okay, Alexandre?
Yes, thank you. So I had 2 questions, in fact, but I think you partially already answered one of them. So it was exactly concerning the possibility to have very supermassive black holes from the runaway scenario. And at which redshift would the seeds form in this scenario?
As I told you this morning, metallicity matters most, because black holes, if they form from stellar evolution, they have to form in low or poor or zero metal environments. And since the metallicity is a growing function of redshift, because it comes from the supernovae explosions. They have to form at very high redshifts, 7, 10, 30, 20, so very, very distant in the very distant universe, also because you have 1 gigayear to grow a quasar at redshift 7. Though these might be rare, and these are just the tip of an iceberg, and we don't see what is below this iceberg. And but we need a low metallicity. Also, if you want to produce stars and collisions, you need to avoid winds. And so the low metallicity is a key requirement, is chapter 1 in the story of the seed formation.
Okay, thanks. And but just because so usually for POP3 stars, what I see people considering them for the seeds forming at redshift 20.
Yes.
And for higher, for more massive seeds around redshift 15.
Yes. Yes.
So for those ones, for instance, more or less, where would they be?
No, you said right. I was trying to, I don't think that, so it is very high redshift, but it is true that the models are telling that light seeds start forming at redshift 30, 25, in zero metal, in metal-free halos. And instead, the DCBH scenario, the Dirac collapse, is shifted to redshift 15 because you need stars that are illuminating the region, not to avoid fragmentation. And the stellar collision scenario we did our study, is after POP3, and it is at redshift between, say, clustering around redshift 15 and 10.
Okay, thanks. And if I may, just one last question.
Yes, of course.
So actually, it's slightly different concerning the Eddington accretion.
Yes.
So in the theory, what exactly is predicted if you go beyond? So is it possible to go beyond? And if you go beyond, will you go back to the Eddington level or much below the Eddington level?
The Eddington level is a limit for stationarity in spherical accretion. You can violate, and we already see sources that are violating the Eddington limit, the accreting black holes or accreting neutron star in the so-called ultraluminous X-ray sources. So it can be violated. And if you have a large reservoir of mass, so you have huge M dot, radiation is trapped within the fluid and conveyed down to the horizon. So you might have obscured sort of accretion because light cannot come out and increase the mass. The key point is, how can you manage such huge accretion rate? And this is an angular momentum issue.
Okay. Thank you very much.
Thank you.
Now we have Il-Sung.
Thank you. I have a question regarding the Dirac collapse scenario, which is certainly very interesting. But observationally, can this event actually create a significant gravitational wave emission? So someday we can detect, so we could verify that the origin is really due to a Dirac collapse?
I don't think so, in the sense that if these events are at very high redshifts, as we said, 7, 10, 15, unless through Dirac collapse, you have a splitting of two black holes that merge, and this was envisaged in the literature through a bar mode instability in the collapsing stars. You need a lot of asymmetry in the collapse, which is plausible, of course, because in supernova, we know that the centricity, the ellipticity which is causing the emission of gravitational waves is quite small as far as we have from the roundness of neutron stars. And this is a possibility, but if it is in the backyard, yes, if it is occurring at redshift 15, I think it is too weak, unless the DCBH scenario predicts the splitting of the star and the merger, and then maybe we could see it. Maybe I will return to this.
Alexandre, do you have another question, or your hand up is still?
Sorry, I just forgot. Thank you.
Okay, so I think that for now we don't have more questions, so you can continue, Monica.
Okay, I'm really skipping quickly to two figures to deliver the message that if we can detect at a high redshift and heavy seed accreting, but we never have the ability to see an accreting seed. Maybe let me just show, this is a plot that Rosa Vagliante provided me kindly, where it is, she's showing the multi-band spectrum from accreting light seeds at redshift 10, and nor Lynx, nor Athena, nor JWST can really detect these seeds, whereas not even growing seeds, because let me just skip this here. So the message here is that we can see a 10 to the 4 growing seed at redshift 14 with Lynx, but with Athena at redshift 10, we will never get any accreting black hole of 4 times 10 to the 5 solar masses. So we need another messenger. And the messenger for the seeds are gravitational wave detectors, of course. The IMBH regime is proved by the third generations. Clearly you see the sensitivity drops rapidly above 200 solar mass black holes, but we can see maybe starved seed. So here we have a full area of exploration that with Einstein telescope will do. And I remind you that I forgot telling this morning that every year we will see roughly 1 million of black hole binary coalescences. And among them, we do hope also to witness intermediate mass black hole coalescences. The redshift, it depends. Also, there is an issue on how really make the parameter estimation of these high redshift sources. And this is something that you guys, you have to consider in the future. So these are summaries, so I skip and I move then, taking question. I may prepare for the next lecture and maybe we can have also 5 minutes break. Marta, chair, please.
Absolutely, if you will. So if there are more questions, we can ask them quickly, but I'm definitely in favor of a few minutes of break. So Chiara?
I'm sorry, it's always so no, just because I think so you didn't really mention in all this very nice review that you did how they get into binaries, right? But if you want to use gravitational waves as observable, you need to tackle also this problem, how these seeds get into binaries.
Can I answer? The answer is in the next slides.
Sorry, okay, yeah.
Yes, we were talking at the beginning before starting the session. We love dynamics. So.
We love dynamics.
So if there are no more questions on this section, this part of the lectures, it seems probably not for now. Let's take a break. Monica, how many minutes do you want? 5, 10?
we have to go. We can go down to 6:30, so maybe 10 minutes.
Perfect.
Okay.
So we reconvene at, well, let's stay at this point, let's do 12. So we reconvene at the hour.
At the hour.
Sounds good. Okay.
5 o'clock. Perfect. Okay. So let me repeat. Lisa has a rich is rich in sources. That is, it will detect a variety of astrophysical sources. Here I'm showing in dashed line the characteristic strain, that is the sensitivity curve of Lisa, so we can detect all sources that are above this line, like for the sensitivity curves of LIGO and Virgo. And let me remark and mention briefly, we expect to detect a foreground or galactic background of ultra compact white dwarf binaries, or some also neutron star and black hole binaries that are producing this background above the Lisa sensitivity limit around a millihertz. And then these little dots plus stars are individual white dwarf binary in the Milky Way or nearby galaxies that are emitting a periodic signal at the frequency which is twice the Keplerian frequency. So this is not even the spiral, it's just the slow in spiral of these binaries, and the stars are the so-called verification binaries, those that will allow us to calibrate the observatory since we know their physical parameters. Then we have three main sources. Here I'm showing the harmonics of the signal, which is emitted by the so-called extreme mass ratio in spirals, that is a stellar massive black hole, say of 10 or 30 or 50 solar masses, which is orbiting around a black hole of 10 to the 6 solar masses on a relativistic orbit, precessing orbit. It's making many cycles, 10 to the 4 cycles before crossing the black hole horizon, and they can be visible out of redshift 2 or so, or 3, depends. We don't know exactly the rate. Then I will comment this in a moment, but these are the multi-band astrophysics that I'm going to describe shortly. And here you see instead the signal coming from 3 black holes binaries with total mass in the rest frame of 10 to the 7, 10 to the 6, and 10 to the 5 at redshift 3, months, days, hour, minutes before merging. And they are just the subject of what I'm going to tell you in the next hour. But suppose we have seeds, heavy seeds or growing seeds. We don't know whether these are already light grown or just newly formed black hole seeds. If they are in binaries, and I will comment this later on, this is, for instance, the signal that we see in the Lisa sensitivity, in the Lisa bandwidth, with a total mass of 10 to the 5, okay, in the various redshifts. So you can clearly see that we see the inspiral and the merger. But as we move to lighter black holes, maybe seeds or not, of 10 to the 4 solar masses, they are still above, just in the middle of the Lisa bucket. We miss the most important part of the signal, so they are low luminosity objects, and we see just their chirping across the LISA band. And as also it was shown here, and it is shown here, what we can have are the famous Cézanne black holes, that is stellar black holes. Here is 30 solar masses, 300 solar masses. These can be in the LISA bandwidth, and after probably years they can enter a terrestrial interferometer. The black holes, soon after the discovery of GW 150914, which is this blue line, it was clear that a black hole binary of 30 plus 26 solar masses could have been seen earlier in LISA and later in the LIGO-Virgo band. And so one could localize the source better, exploiting the LISA orbital motion around the sun, and see and detect then the merger in the LIGO-Virgo. So this is, I want you to have this picture in mind. Let me return, well, let me just say this. So imagine, I want just to make a movie of what may occur in the universe. Suppose we are in the high redshift universe, and seeds are forming in dark matter halos. Not in all. The occupation fraction initially is very low. But then halos merge, and so they carry a single seed. But then there's a halo which is carrying another black hole. And then the merger of these two halos for sure may bring a dual black hole binary. That is, there will be two black holes in this halo. The black holes are growing by accretion. So here they are coalescing and doubling the mass and changing the spin. Then this is single black hole is going to accrete. Then there is another halo with another black hole, and so on. We may form our massive black holes in our universe. And so along this track that is famous because it was a Marta cartoon, we have used the information that galaxies are assembling from the bottom, from low masses to high masses through mergers, major when their mass, the mass of the intervening black hole halos are comparable, minor when the mass ratio is below 1:4, and also halos are also accreting gas from the filaments of the cosmic web. So we have a cosmological setting, and here is the LISA horizon, cosmic horizon. Here is again a waterfall plot where on the x-axis we have the total mass of the binary black holes in the source rest frame, and here is redshift, and these colorful contours, these are lines of constant signal to noise ratio. 3000, huge. Here is 500, here is 200. Then, since we say that we detect a source when the SNR is above 10, then this is the entire sensitivity window of LISA. And look here, the LISA will be sensitive mostly to black holes of 10 to the 5 up to a few times to the 7 up to redshift 20. So almost the entire universe. So these are light black holes of the supermassive. So these are supermassive black holes in the low mass tails. And so these are the ones for which also electromagnetic information are quite poor. And there is really a paucity of information that can be gathered by LISA. And so here is just a cartoon. So imagine that here I'm pinpointing places where you form, say, a heavy seed. There is a heavy seed formed at redshift 14. They merge, and this is a LISA event. And then I can explain both the quasar near the epoch of cosmic reionization, that the quasar at the cosmic noon, when the peak of the AGN activity is present. This is the same figure. Here I want just to say that accretion could alone explain high redshift quasars, provided accretion is very fine-tuned. But we believe that halo-halo mergers are conducive to the formation of black hole binaries and their merger. If they succeed in going very close together for gravitational waves to drive their emission, they're in spiral. This is a recent paper we published with Rosa, where we try to merge information or unify information between LISA and Einstein telescope. Rosa Valiante as a semi-analytical model for the formation of seeds and for the formation, the triangles, no, the squares, sorry, are, no, the triangles, I forgot. The triangles are associated to heavy seeds, and I forgot, aiuto, non mi ricordo più. Well, let's say in a simple way. Here are seeds that are forming in binaries, not because they are seeds that form in binaries as most of the massive stars are forming. These are seeds that are the outcome of halo-halo mergers, and in which multiple interaction, triple interaction among halos are favoring their pairing. We used recipes for the dynamics that can bind these seeds, but I want to be honest, it is extremely difficult to imagine how binary seeds of POP3 stars or population 2 stars are forming in a cosmological scenario. Maybe the binary are all formed just as binary stars are forming. And so this is a great, great uncertainty. The yellow triangles, when the border is white, now I recollect, are black holes that are merging, that are coming from heavy seeds. So it's still somewhat difficult to compute the merger rate. We said a few per year. It is always the story. It is a few per year. But it is clear that, especially in the Einstein telescope bandwidth, we will be dominated by stellar binaries and POP3 stars. Whereas in the LISA band, we could see either the evolution of light seeds, which are produced more abundantly, or heavy seeds that are rarer. And we can explain the three quasar, one at redshift 7, one at redshift 2, and one at nearly 0 redshift. So this is just to show that if we can statistically compare events in the LISA and in the ET band, we might indirectly reconstruct the growth of the black holes. This is just the beginning of a deep investigation where we would like to include a lot of input physics, which is very complicated to include because we are dealing with stars in halos and mergers of halos, so the dynamic range is really huge. And I can stop here before going on.
Okay, so in the chat, there is something, I'm not sure if it's a question or not, from Vanita Krishna. Is there a question? Okay, probably not. So Il-Sang?
So I have one question regarding this, the redshift evolution of the seed population, especially in the context of the halo mergers. How realistically you deal with the actual merging of the two binaries within the finite time, so we will be able to see them within the observable universe. Is that already taken into account? This
it is taken. Modeling? It is taken in these dots. We count the merger that are occurring at that cosmic time.
Yeah, okay. So then my question really is, how do you actually trace back to the earlier universe so you are sure that those initial seed actually form okay.
So the semi-analytical model is taking is construct to reproduce. This is a very rare massive galaxy, or massive probably galaxy cluster of 10 to the 13 solar masses at this redshift, and you trace back with your semi-analytical model. So you start with halos that you believe are in place at redshift 16. You have a recipe for the inflow of gas. You have a recipe for the initial mass function of the black holes, which is flat over a range, say between 100 and 300 solar masses. And then you keep on following along the merger tree, which halo is going to merge with which. And we use as dynamical model for the pairing of these black holes triple interactions that I don't know whether I have time to describe, but is like you have two black holes in a binary, and the third black hole can excite and accelerate the merger through a dynamical process. But we have seen that the dynamics of seed in high redshift galaxies is extremely erratic. I hope to have time at the end to make a comment on this because it is very important. So how really two black holes that are inside halos that are merging can really reach the gravitational wave-driven domain is a big issue. At all levels, I would say, and especially for the light and heavy seeds, not for the very massive seed. So 10 to the 6 or 10 to the 7, I think we can deal with their merger. But these light black hole are very difficult to take them down to the gravitational wave-driven domain.
I see. Thank you very much.
You still have your hand up? Okay. Is there any other question this time? Okay, so I think you can continue, Monica.
Yes, for the next 10 minutes, I want to just give you sort of a flavor of the dynamics of merging galaxies. First of all, on the left, there is a very beautiful inventory of real galaxies that are hosting accreting black holes. But here you see just the beginning of the merger of the two galaxies. So the black holes are still really very, very far apart. we know they exist and galaxies merge with their black holes at their center. And we call these dual AGN. But, well, this was a movie, but it's just for fun. This is a movie done with Alessandro Lupi, that we have these two black holes in two merging disks, that there is a burst of star formation. We are modeling under various assumptions their way to come closer and closer. The issue is really important because knowing how fast two black holes can merge and produce a gravitational wave transient is an issue, and is a very severe issue because, for instance, if you want to have, so the Schwarzschild radius of a 10 to the 6 solar mass black hole is 0.1 microparsecs. So where you consume the merger when you have two, this is 1 microparsec, 10 microparsecs. The coalescence time by gravitational wave emission scale with a very high power of the binary separation A. A is here the binary separation. It is scaling also with a high power of the total mass of the binary. So the more massive the binary is, the shorter is the coalescence time. But if the mass ratio, here is the symmetric mass ratio, is small, the coalescence time gets longer. And if the eccentricity of the orbit is large, you can sizably reduce the coalescence time. I didn't touch the issue of the eccentricity, but it is an issue. But just to give you a feeling, for the gravitational wave domain to fully control the inspiral, we have to take these binaries down to a fraction of a microparsec. And 1 parsec is the distance of the sun to Alpha Centauri, the first stars we have nearby. And well, the cosmic time here, I've selected 0.3 gigayears, but notice that the coalescence time, so is really, for this short time scale, we need a very small separation. But if you revert the relation, the AGW goes like the T coalescent to the 1/4. So the scale at which gravitational waves intervene is almost of the order of fraction of microparsecs. But the mergers started on kiloparsec scales. And we have been trying with Marta and to understand which are the mechanisms that take first to galaxies to coalesce is cosmology. The baryonic component of the galaxies merge because they experience dynamical friction against the dark matter halos. Then, and this is occurring on, say, a scale of 10 kiloparsecs. Then we have to bridge a scale that from 10 kiloparsec take you to fraction of a milliparsec. And in all this range, we need additional torques and dissipative processes that are not related to gravitational wave emission. If I have time, I will depict these steps, but let me just give you the classical and still somewhat old view, but it is for beginners. And this is the story. When you have two black holes in an already merged galaxy, the black holes have a mass of 10 to the 6 solar masses, say, and they are very massive compared to the stars of the host newly formed galaxy. And they sink toward the center of the galaxy by dynamical friction. And as they sink, the time scale gets shorter, shorter, and shorter. But at some point, they form a Keplerian binary when the mass in stars becomes smaller than the mass of the binary. At this point, like a sort of in the formation of the dynamical formation of binary black holes that we have seen this morning, the two black holes are interacting with stars, individual stars. So each single star, imagine you have the binary, they are revolving, and then a star coming on a low angular momentum orbit is passing through the binary, slightly taking away energy and angular momentum. And when you have a number of stars comparable to the mass of the binary, we say, hardens and can transit into the gravitational wave-driven decay. How many stars are there to make this last job? It has been an issue. It seems that it is possible. And let me just show to you, just to give you the sense of what a collision is. This is a simulation by Capello, did by Marta, of two disk galaxies with all these parameters, with the halo of dark matter, of this mass, a bulge of this mass, a gaseous disk of this mass, and a primary black hole similar to the Milky Way. And you let go the simulation. Okay, this is a 1-to-4 merger between two disk galaxies with a gas fraction of 30%. And so you begin with the two galaxies far away. This is the first closest approach. In the closest approach, you excite tidal phase. The galaxies are going away. They reach the highest separation, and then they return back. And after only these few passages, after 1 gigayear exactly, at the second apocenter, you have really a huge perturbation inside the star. You are forming star. This is a way to shake galaxies and form galaxies. Then at the third apocenter, you end up having a new galaxy, okay, which is sort of stationary after 2.2 gigayears from the merger. The resolution of the simulation is such that one could trace the black hole separation, okay, the black hole separation relative to the center of mass down to 10 parsec, which is a very good resolution for a simulation of a galaxy, of two isolated galaxies. You see here that the two black holes are dragged closer because also the bulges of the galaxies are merging. So they are enshrouded by the mass of the bulge. So the bulge is really, I don't know whether you know, but it is just the sphere of stars that are making the central region of galaxies. And then you sort of can't anymore, or you can follow the evolution, but then you are hitting the resolution limit. This is the evolution of the secondary black hole, which is similar. I was willing just to show that along this merger, you are forming stars because you are shocking interstellar gas and you are really making episode of star formation at a rate which is not so exciting, but 1 per year. And the accretion rate is erratic, but the two black holes are also merging. Indeed, we see dual active galactic nuclei. And it may be that the secondary is accreting more than the primary. If you change the mass ratio, it takes longer to the black holes to reach the parsec scale. But after this, you need either a gaseous disk or the interaction of stars to go into the domain of gravitational waves. This was just an example. We may return back, but this kind of simulation, as well as cosmological simulations, unable to compute rates of merger. And this is, again, another work by Marta, where we compute a cumulative rate of events from a high resolution cosmological simulation. And here you see that the peak of the merger is around 2.4, because we introduce all the potential sources of time delay in the formation of the binary, and it's shrinking and hardening. And there are many papers, also one which is considering more complicated dynamics. And here is the expected rate of events detectable by LISA in 4 years of life in various models, from a model with light seeds and heavy seeds. And you see that the bulk of the rate is around 2 and 4, but we might have or hope to have detect events at higher redshift. And this is distribution of the Chirp mass, which gives you a sense of which are the masses which are involved in the mergers. We are, as the LIGO-Virgo collaboration was before the discovery of the first sources, where the rates were uncertain by a factor of 10 or even more. So Lisa will tell us how things are going. So I may stop here, because now I'm then moving to the electromagnetic counterpart and then return to dynamics, because I thought that multi-messenger astrophysics was more interesting for the audience.
So do we have questions here? Yes, Eric?
Hello. So I'd like to ask a question. In the case where we have the binary that is stalled, right? That doesn't make it through the last parsec. I presume that having such a binary at the core of the galaxy may have effect on the appearing structure of the galaxy itself. Is that something that we can search? I mean, is this stupid? I mean, naive on my part?
No. Well, if the binary is stalling and they are sufficiently massive, and it is nearby, then you can, through the light curve of the dynamics, you might expect some modification in the shape of the galaxy. But there's much more hope if you see the binary, an offset black hole in a galaxy. So if it is not right in the center and it is accreting with a spectrum of an AGN, you might say that this is maybe there is a stalled binary, because it is likely that it was the outcome of a merger where there were two black holes. The dynamics of these black holes is quite stochastic, and there has been an explosion of papers saying that not even the black holes could be wandering in the outskirts of galaxies, but they could even be sort of, displayed significantly. And if a black hole is going into the halo, it hasn't much gas to accrete. And it's very difficult, at least this is my answer, to detect any kinematical signature in the stellar profile.
Well, yeah, can I have a follow-up question here?
Sure.
Where the point where I want to come to is knowing the shape of the galaxy that we see in the nearby universe. Is this compatible with a significant fraction of them being with a binary of massive black hole in their core? Are there been...
Okay, I have two questions. I have two answers. The first is the contrary to your question. They say, do we have evidence in bright galaxies that there has been a merger? And the answer is yes, because there are very bright elliptical galaxies who are showing a stellar profile with a core and not a steep increasing stellar density. And the core is consistent with the mass ejection of stars, exactly the one needed to make the binary merge by the individual scattering, because every time a star is interacting with the binary is ejected, and it may return if there is some replenishment of these stars. So in very bright galaxies, there are these so-called core galaxies that are interpreted by the outcome of, in their core, of a successful merger. But the problem here is that these black holes are very, very massive, and not the one LISA is going to see, 10 to the 9, 10 to the 8 solar masses. So now you know that the pulsar timing array is trying to detect the gravitational wave background from binary away from coalescence, far away from coalescence, so a century or even more. These are already Keplerian binaries, and we will know whether this process is successful. But we don't have evidence of offset black holes because they are very difficult to, so we don't have a signature. People are searching for these. So you where were you willing to go? Can you remind me back?
So you're asking what I was suggesting. I was suggesting, you know, to use survey, galaxy survey and their shape to ask the question whether this the shape that we observe for nearby galaxy is consistent with them having a signal black hole in their core instead of two.
Perhaps, Monica, so I think that what Eric is asking, if I understand correctly, is whether we could see the dynamical signature, so in excess of mass, close to the center that would represent the second black hole. Is this what you're asking? You're muted. Eric, you're muted.
No, what I was, you know, it's really, it's probably a very naive intuition of mine, but the luminosity profile of a galaxy is possibly affected by the presence of two massive black holes in their core, right?
Indeed, indeed. Yes. But the sphere of influence of a 10 to the 5 black hole is so small that unless it is in your backyard and you use probably high resolution surveys, you will never get it. So the answer is no, it's not from the light profile that you can detect LISA black holes failed in pairing.
I see, okay. Well, this is the...
I don't know if Marta agrees with me. I prefer...
No, completely. So, and especially if you're talking about binaries, so I think that Monica distinguished between binaries and duals. So if something is far away from the center, is what Monica was saying, that people are looking for this. But when you get very close to the center, the seeing, so the angular resolution that you have is simply, I mean, you would see, even if there are two, you would see one. So I think that's the main problem. So now, Ilsan.
Thank you. So regarding this picture of the scattering between the binary black holes and the stars to have a separation smaller and smaller, I can naively imagine if stars is scattered by the binary black hole and ejected with some kinetic energies, eventually it has to come back to replenish for the further scattering. Then I think the potential well of the host galaxy should be deep enough to actually have those stars fall back. So in that sense, is this safe assumption that this thing will work in general for the majority of the mass range of your galaxies, or is it only valid up beyond a certain mass limit?
I think it is beyond this. So it is an open issue. You said you understood perfectly the issue. It was an issue that lasted for 40 years. And the answer is that in the early days, it was believed that when a star was scattered by the binary, given the large mismatch in the masses, the star was ejected and didn't return back. And it was claimed that only relaxation processes means that when you are in a dense stellar environment, the energy of each single star is not necessarily conserved over a time scale, which is called the relaxation time scale, which can be 1 gigayear, but can be longer than the Hubble time. And so there was the claim that there are only few stars that cannot really continue the hardening of the binary down to the gravitational wave regime. But recently, when it was recognized that the merger of two galaxies is not a round spherical galaxy, as soon as you have residual rotation that you should have, the topology of the orbits of the star is changing, and the stars, there are plenty of stars that are passing through the central regions of the newly formed galaxy. So it's not anymore a problem. There are enough stars to make the way down to the gravitational wave regime. This is rather clear if you have 10 to the 6 solar masses black holes. We studied recently using scaling relations, we might have merging time of a few gigayears, but it depends quite sensitively on the stellar profile in galaxies that are not so well, that are irregular, and so they don't have, they are not as simple as an elliptical galaxy, say. And so it's still an open issue. So I would say that probably a 10 to the 8 solar mass black hole can make it, and pulsar timing array will tell us. 10 to the 6, maybe we need gas or other processes.
Thank you.
If I have time, I can return or discuss on Friday if you are interested. Then I was willing to change the subject and go and move to the multi-messenger view of massive black hole binaries. So I asked you to make really the reason why it is so important, this issue. Chiara knows exactly why. Is that if we detect an electromagnetic counterpart, we can really probe the cosmic expansion with a new messenger, gravitational waves. I think that in the cosmology lecture we'll cover this topic. But let me remind you just that when you see the coalescence signal of two massive black hole binaries, you infer the luminosity distance. And if you see the counterpart, so the galaxy which is hosting the merger, from the atomic spectral lines, you infer the cosmological redshift, and then you measure the Hubble constant. This is doable with massive black hole binaries, with MRIs, also as well, if they have a counterpart because they are embedded in a galactic disk of gas, and probably most of you knows how we will be going to measure the Hubble constant statistically with stellar mass black holes that do not appear to have any counterpart. So here, cosmology is a driving motivation for searching for an electromagnetic counterpart. And, but it's also, from the astrophysical point of view, very interesting because we don't know yet, no transient AGN-like emission has been ever observed that could be attributed to a coalescence event. So let me say explicitly, we don't have a short gamma ray burst analog for these mergers. Of course, you have to scale in time by 1 million because we are dealing with huge black holes and the light travel time is 1 million times longer. But I ask you to really imagine that we are almost about to merge in the pre-merger phase. And the binary is surrounded by what we call a circumbinary disk. There has been a lot of interesting studies in recent days. And let me quickly summarize the key findings. So imagine you have a binary of two black holes, massive black holes, surrounded by a circumbinary disk. This disk would be the accretion disk over a single black hole if there were not a binary. Many simulations here, I have tried to put some references, have shown the following, that the two black holes surrounded by the circumbinary disk deposit orbital angular momentum inside the disk that can be either self-gravitating or non-self-gravitating. Let's skip this detail. And the quadrupolar torque excited of the binary is trying to excavate a hollow region, a cavity surrounding the binary. Angular momentum is transported out by spiral waves that you can clearly see here. This could be a situation where the two black holes are still, far from coalescence, not in the LISA band, but they could be in the pulsar timing array band if they are massive. And what the various simulation has found is that in reality, the cavity is filled of gas. And it follows, so there is a sort of coupling, which is described in this slide, between the quadrupolar torque that the binary is exerting on the disk and the fact that the disk is viscous, and so thanks to viscosity, it follows the binary as the binary is shrinking due to this torque, that gas dynamical torque. The disk inner rim follows the binary. And so the two black holes migrate inwards if the disks are really geometrically thin, but the gap is filled of a lot of gas, hot gas and filaments. So this is one of the most recent GR MHD simulations by the group of Bowens, Campanelli, of a circumbinary disk around a binary where the two black holes are just on a circular orbit and are not in spiraling. The binary has always the same orbital frequency. But you can clearly see that there is a sort of lamp asymmetry in the pattern. So the two black holes are constantly fed by two mini disks, okay? This is just not a black hole, but it is the excision of a region in the grid of the gravitational, of space-time. So the message I want to deliver is that the binary naturally excite highly non-symmetric structures. Gas is ejected, is shocked at the inner Im and returned back. So there are streams linking the circumbinary disk to the two mini disks. So if there is a circumbinary disk under given conditions, the binary, even during the in-spiral, when it enters the LISA bandwidth, could be accreting. That was something not obvious 10 years ago or more. And there is general consensus on this. Then Tang and Dascoli, two different groups using different, one is post-Newtonian, one is full GR simulations, have tried to derive what would be the X-ray spectrum, the broadband spectrum. Let's look at this one by Dascoli. So the claim is that in X-rays, you would see the accretion coming from the mini disks, then very hard X-rays from the hollow regions, and instead at optical frequency, the light coming from the circumbinary disk. And also they found that there is variability which is commensurate with the non-symmetric fluid patterns. For instance, the bit frequency between the orbital frequency and the lamp. There is this asymmetric lamps here. So you would expect also a modulation. We don't know how these really, whether these are reasonable spectra, but is the first important effort made by the community. So we decided with Alberto Mangiagli, Alberto Cesana, Marta to study the capability of localizing a source with LISA in the three stages. The pre-merger, where this type of modeling is suggesting modulation at some frequency, maybe the best would be an orbital frequency, if there is an unequal mass binary that is tracing the chirp, the gravitational wave chirp. And we don't know whether the X-ray luminosity is rising during merger or decreasing, because the mini disk here will become truncated by the mutual tidal field. So the Roche lobe of surrounding the Roche lobe defining the extension of the disk shrinks, and so you might have less and less matter. There is outflowing matter in between the two Roche lobe overflows, so it is a complicated stuff. And then we would like to see at merger and the post-merger, the rebrightening of the disk or of a jet. And we decided to study the localization abilities of LISA by asking for the GW community to give us a waveform that would contain the higher harmonics. Though they are not really important in the spiral, but are more in the merger. I like very much this figure by Sylvain Marsat, which is showing what? This is a binary with this parameter here. This is the sensitivity curve of LISA. And this is the spiral and the merger. If you include higher harmonics, and you know far more than I, both the odd and even harmonics, especially at merger, you see that you have contributions that can make the source far more brighter at the end than without, much more brighter than just taking the quadrupolar term, the leading term. And in this study, it was shown that higher harmonics narrow down localization uncertainties for unequal mass binaries that should be a common place, because identical binaries are not produced by nature in this type of scenarios. And apparently the L equal M harmonics break the degeneracy between the mass ratio and inclination, and the odd harmonics break the degeneracy between source location and luminosity distance. We studied separately the inspiral, and we are studying with Sylvain the merger. Let me show the outcome. When we studied the inspiral, we took a statistical approach, not just a few binaries. And here is the outcome. We simulated a suite of binaries, keeping fixed the total mass, 3 times 10 to the 5, 3 times 10 to the 6, 10 to the 7 solar masses at a fixed redshift. And we let vary all the parameters, mass ratios, random spins, times of coalescence. So we could really sort of imagine that every single source has an intrinsic scatter in the way it is detected. Polarization angle, inclination angle, all averaged as usual when we do averaging for measuring the SNR. And we did the parameter estimation on the fly from 1 month down to 1 hour, because after 1 hour, we see the merger that we could not model because we hadn't the full waveform. And we scaled the SNR taking a classical Taylor, I don't remember, it was a Taylor waveform, one of the usual waveforms are used for this type of signals. Let me show. These are at redshift 1, and you can clearly and beautifully see that 1 month before the merger, this binary is already sort of detected by LISA. The black line is the median, and the blue is the 68 percentile and 95 percentile, the red. So the signal to noise ratio grows up to several hundred, and at merger is 1,000. These are really the binary that we would like to use to see deviation from GR. And this binary, which is slightly heavier, is entering slightly later, few weeks, but it is an even more brighter. And this 10 to the 7 binary is entering a week. It's less bright because we are tracing less cycles, because we are already hitting the barrier at low frequencies in the LISA sensitivity curve. And this is delta omega, so the sky localization uncertainty. And the sky localization uncertainty initially is really huge. It is 100 to 1,000 square degrees. As the merger, the spiral is continuing and progressing, the chirp, of course, the localization gets better and better and better, mildly exploiting the orbital evolution of LISA. And for this binary, 10 hours, but only 10 hours before the merging, it is entering the LSST field of view, the Vera Rubin Observatory for the transient sky in optical. But it entered the 0.4 square degree, which is this line, which is the field of view of Athena only at merger. And the situation is even a sort of worse for more massive black holes, because they are staying less in band. And look at the spread, which is associated to the inclination angle, degeneracy with the luminosity distance, whether the source is on the top of the LISA plane or it badly oriented. So LISA has no blind areas, but of course it depends on orientation. And so it depends if you are lucky that you are in this condition or in the worst conditions. And we found that, of course, the chirp mass and the mass ratios are really well determined within 10% or even 1% accuracy before the merger. So we know that we have a binary with this mass ratio, and this chirp mass is fantastically determined. And so we understood that only if we have what we call a platinum binary, that is a binary very nearby and light, this is a binary at redshift 0.3, okay, we could have that the binary is entering the LSST field of view and probably also the SKA field of view. And then with Athena is entering 10 hours, the sufficient time to alert Athena to point in the 0.4 square degrees where it can find where there are many galaxies, but you hope to see a periodicity or a brightening that is unusual compared to the AGN variability. This platinum binary is really determined. This is a corner plot by Sylvain that is telling us that the chirp mass, the mass ratio, and also the individual spins are really beautifully determined. 3 hours before merger, the red contours, and at merger, okay? And the true signal is at the cross of these corner plots. So this would be really like GW170817, a nearby unexpected merger that would be a piece of cake. Fantastic.
Sorry, Monica. Chiara has missed what was the black star in the plot.
The black star is where we know where the parameters of the source are. And this is the reconstruction by Bayesian analysis.
Sorry, the previous plot.
In the previous plot, the the star?
Yes, the star.
The star is just that we would like to have 3 days of alert to be sure that we are downloading the data from LISA, and we are willing to see if there is some clear periodicity that can still be preserved.
Okay, thank you.
This platinum binary, this is a plot again by Sylvain that is going the sky localization uncertainty as a function of the inclination angle of the binary. And depending on where the binary is, you have really a large spread in delta omega, okay? But most of the at merger, the sources within the Athena field of view. And for a smaller fraction of sources or probabilities, it can also be seen with the XI few, that this is an X-ray integral field unit, which is a spectroscopic unit with a resolution of 5 arc minute in space and a high resolution in energy. So we could take very well spectra at merger. And instead, a heavy merger may never enter the field of view of Athena, but it can be seen by optical and radio telescopes at merger. Here is the cumulative distribution of delta omega for this platinum binary, which really can be pinpointed quite well by an X-ray telescope like Athena. A golden binary can be detected by Athena, and only less than 20% of the sources is really pinpointed by Athena with a very high precision. And for the heavy one, we have only that 50% of the binaries can really enter the Athena field of view. That is a natural way to select a rebrightening at merger of an event. And last figure, and then I take question, which I really love, is this one, where we made this exercise. The X and Y axes are the longitude and latitude of a source, to show the ability to pinpoint the location of the source, 8 days, 1 day, 3 hours, and at merger. And the beauty of a very nearby 10⁵ solar mass binary is that even 8 days before the merger, there is one single patch in the sky where the source is localized. But as far as I understood, so it is always in the same sky location, and then you narrow down the position as time is progressing. But instead, if you have a binary of 3 × 10⁶ at redshift 1, there is this so-called sky multi-modality. So you don't know, there are 2 places. So the star can be in 2 places. And for an X-ray telescope, one cannot point one region, but it cannot point the other one. And so they are in 2 hemispheres. And it is very well located at merger. And for this 10⁷ solar mass black hole, it is very well located at merger, okay, very well located, as I said before, But instead, during the spiral, you have so multiple images, say, of the event that it is, in my view, impossible to localize the source. So the message I want to deliver, which is in this last figure that was done by our group and Alberto, in particular Cesana, the message is that we can really see at merger within the Athena field of view all the binaries that are within this green line, with a strategy in measuring the X-ray luminosities, okay? So between 10 to the 5 and a few times 10 to the 6, they can be localized by Athena. And then we need also to have optical follow-up. The pre-merger requires really rare platinum binaries for which we don't know exactly which is the rate. And so the good news that at merger, we have a single patch in the sky to search for and try to see if we have the rise of a corona emission or an X-ray or a jet that can localize the source out of redshift 2, 3. This is the outcome of this investigation, and I stop here.
So, do we have questions on this part? Okay, while other people think of questions, can you re-explain, perhaps I missed it, the rebrightening?
The rebrightening is something, I think it is a project that we have to do together. The rebrightening is the time during which accretion, now you have a single black hole instead, and you wait for, and it is in this hot cavity, the black hole, the new black hole, neglecting recoil, but even with a mild recoil, is dragging part of this disk. And the disk rebrightening is the accretion onto the relic black hole.
Okay, so a follow-up while other people think. So you just showed us these results for the platinum golden binaries, but so how does it change in the case of recoil? Because so you pinpoint the position of the merger, but if you have recoil, then the follow-up with other telescopes will not be in the same position if the recoil is sufficiently...
Yes, but if you look at years after, but if you look at weeks or months, the black hole is still there and it is dragging the bound material. So you will never see offset. You will never see the offset.
Okay.
Because if you look a year after or 2 years after, in the same patch of the sky, how do you really know that some flaring of an AGN was just associated to the gravitational wave event? The beauty of short gamma ray burst is that after a second, you have the gamma ray burst. Okay, so you have a sort of a coincident concordant emission. Here you might wait a month, okay? For the jet, there is a paper by a Chinese group, but there is Mejaros.
Yeah.
They studied the jet launching. I think that there is a lot of work to do there with the people that are working like Ghirlanda or Salafia to the short gamma ray jets because there is no obvious scaling.
No, I agree. Okay, but sorry, I was monopolizing your time. A question from Samuel Ronchi. Do you want to read it or shall I?
Yes, I can read it. if we search for electromagnetic counterparts of massive black hole mergers in a given patch of the sky, how is it possible to distinguish between these mergers and other contaminants? Do we expect a periodicity in the signal or a specific spectral feature?
Indeed, if we see the pre-merger phase, the idea was to see sort of this is the periodicity in the X-ray light curve. And this periodicity that goes in tandem with the chirp is a unique signature for sure. But to carry out this time series analysis is not so easy. But if this is there, it would be fantastic because you have really a match with the chirp. In the post-merger, where we have the ability to localize within 0.4 square degrees, in X-rays, there are many galaxies. And so I think that this is what we probably are going with Marta. We should understand which is the host. So if you go into the delta omega of the uncertainty of Athena, you can find probably thousands of X-ray sources. And maybe by the time LISA will fly, we will have these type of simulations so well done, provided we are doing the physics well, that we might have synthetic spectra to compare. But this is an issue. This is, as you pointed out, is a critical issue. So it is really challenging. But since that would be of paramount importance, in 15 years from now, maybe we have more knowledge on this. Also, spins are not there. And can you imagine also the processing spins during the merger? That would be a signature, very important.
One more question from Il-Sang.
Is there any scheduled or the planned spectroscopic follow-ups, especially for the recooling event?
I think that they should be planned. If the platinum binary, for instance, can be seen by this X-ray integral field unit, you can really do fantastic spectroscopy. So really you can understand, see the spectra, because if more than 60% of these platinum binaries are there, they are within this field of view, which is 5 arcminute. You also see the galaxy. So it is really, it is like GW17, 0817, a miracle. It was a miracle.
Well, let's cross fingers also for LISA. So Samuele Ronchini has his hand up. Is it the leftover from before or another question?
I will have a second question if possible.
Mm-hmm.
Yeah, I wonder if the inclination angle of the binary is influencing the, let's say, the intensity of the electromagnetic counterparts. Because I imagine if there is a beamed emission, so there is a Doppler factor in this emission that is enhancing the outcoming emission, this is influencing the detectability of the source.
Yes. Let me answer in this way. If you are seeing face on the binary, okay, since all simulations have shown that the black hole is really, since it is rapidly rotating, the new black hole is launching a jet. And if you are viewing the binary, the X binaries, the new black hole, from the face on or face off, you might see the jetted emission, which is broadband and would be fantastic. You are seeing the non-thermal emission, though it takes a while to produce this non-thermal emission, because the jet initially is just is a Poynting flux, and it has to interact with the matter to produce and accelerate the electron and positron pairs that are producing the jet. But it would be loud in GW, because it is the loudest system, and loud in jet emission. If you see this edge on, it would be less loud in GW, but you could see in the inspiral Doppler beaming and Doppler shifts. If also it is unequal, the secondary black hole is moving at near the speed of light, and it's creating a sort of a blue and red shifted emission that could be very interesting to detect. But I said the pre-merger, the inspiral, we were more, in the early days, we were more willing to see at Redshift 2. Instead, here we are afraid that we won't be able to localize the source.
Okay, thank you very much.
Okay, so if there are no more questions, perhaps Monica, you can continue for a few minutes.
I'm dead, but anyway.
No, I mean, it's 18:22. So if you want to continue, we can, or we can, it's up to you.
Just a very short flash of returning back to dynamics. What can I tell? Also, the students should be very, very tired, but let's just, maybe we can leave it if they are interested for Friday, if I'm also able to move the examinations. I want to tell that the more we studied, well, that was the synergy between Einstein telescope and LISA, but I let you in the PDF to enjoy. I love this figure, which of course I made. Returning to the dynamics, I want to say two words. Close your eyes and open again the eyes, and imagine you have one central black hole in the middle of a galactic gaseous disk here, and the secondary, which is orbiting around. The disk is producing stars, is fragmenting. It's the place where stars are forming, and there are clouds. And we have found that if the disk is smooth, the secondary black hole is making dynamical friction and is sort of merging with the primary. But it can be scattered off plane by the clumps of comparable mass, because in a sense, the interaction of a clump and the black hole is like a two-body interaction or a three-body interaction. And this is broadening the time scale of sinking. You might have condition that you accelerate, or condition where you instead let the black hole wandering. And in another simulation by another group led by Lucio Meyer, they have seen that when you have these clumpy disks start forming, the black holes secondary can be ejected. And so you have a wandering black hole. So the dynamic is not smooth because the underlying background is not smooth. Here I've prepared for the spin alignment, but I don't want to do this. This is again another example of another simulation of a high redshift galaxy, which is mostly composed by gas. And they made, Elisa Bortolas made the example of inserting randomly a number of secondary black holes in this quite clumpy galaxy. And she has seen that if this galaxy is forming a bar, a gaseous bar, the some of the black hole is dragged into the center, others are instead ejected. So the prediction of the existence of wandering black holes is a sort of robust prediction of dynamics, and the delay times are still uncertain. So sometimes you make the merger more rapid, some is delayed. And in particular, in this paper with Marta and Hugo, we simulated two cosmological high redshift halos at redshift 6, where in each halo or in some there are seed black holes. We have seen that the dynamics of a black hole of 10 to the 5 solar masses is relatively smooth. But for the black hole of 10 to the 4, the black hole is never at the optical center or the center of mass of the host galaxy. They are off center quite naturally. And look at how the stellar background and the gas background with time is varying, because we are in a fully dynamical situations where clump are adding. And so the underlying gravitational background is intrinsically stochastic, making stochastic the orbit. Do they pair and form a binary, these seeds, at very high redshift that is fated to coalesce? This is, I think, it is a question mark. And I think we will need years of investigations to be prepared for LISA. And I stop here. And I thank you for being so patient.
Thank you, Monica. It was wonderful. So it's 18:28, so perhaps we can take one quick question, or if there is anything left.
Maybe I can ask one question if no one else has. So this goes back to where you were showing the error on the sky and different facilities. This plot. So the following one. So here okay, so I understand. So the error on the sky is a function of the inclination, but I don't understand what are all these points. How did you obtain all these points?
I think I have understood what Sylvain is making. He's taking this binary, you know, 3 times 10 to the 5 mass ratio. I didn't write the mass ratio is 0.33 at redshift 0.3. And as you know, you don't have the way you see the binary depends on the sky position, polarization angle, and inclination. And he said, if I change the inclination, I change the SNR, and I change the ability of breaking degeneracies in the waveform, which is one of the best waveforms, as far as I understand, are on the market with a higher order mode. And it's telling you that these are the probabilities of localizing the source, the very same physical source, depending on the way we see the source. And since the bulk of the dot is below the WFI, which is the field of view of the wide field instrument on Athena, you see that the bulk is well within the Athena field of view, which is in a sense equivalent of saying that 80% of the binaries of the same binary has the probability of entering the Athena field of view, and a small fraction into the narrower field instrument. And so, and also to surprise also to Sylvain, when you change the latitude and colatitude, also you have a widespread in the delta omega. So delta omega is sort of the worst parameter of our binaries, because for this system, we know exactly everything: masses, spins, individual spins. These have a SNR of 1000, yet the location is troublesome. And the reason is that is the same story. We need to enhance sort of the sensitivity at low frequencies to catch the binary early on to improve localization.
Yeah, okay, very clear, thank you.
And Eric is asking a clarification. I will just read it. So the first order, this follows 1 divided by the SNR squared?
Yes. Delta omega, yes, yes. Crudely, yes.
Okay. So Monica, you will let us know if you can join on Friday morning on Gather. The meeting is planned for if I can, after starting at 11. So,
and it's lasting for how long?
Until lunchtime, more or less. So,
okay. So I do my examination, but I take an empty slot for the meeting.
And so more people can ask questions to Monica there.
I will be there and exposed to the question the students would like to be answered.
Perfect. And so I think at this point I can just only thank you for your time and patience and for giving us all this wonderful overview.
Thanks to the organizers, to you, Chiara, Eric, and it's really a pity I'm not in Paris, having in front all the students. Let's hope for a brighter future, and all my best wishes to the women of the day. And thanks for also the student. Let me thank the student for being so patient with me. So bye-bye and see you soon.
Thank you.